Alright, so next section of the chapter. In section 3 we learned about our division algorithms, long division, synthetic division. What this is going to lead to, and I know I alluded to it last time, but it's going to allow us to find x-intercepts, zeros, roots, which all mean the same thing here, first thing in the notes here. So this is going to improve our ability to sketch polynomial functions. And I know that's why you get out of bed in the morning just like me. So again, key note here at the beginning, zeros, roots, and x-intercepts are all the same thing. They're where functions cross the x-axis. And these division algorithms that we learned, this is what's going to allow us to do that. And that applies to any polynomial. The next thing that I'm going to have you jot down in your notes here. So I'd recommend here, take a pause on this screen, make sure you have this down. So Descartes' rule of signs, to describe what this is as you write it down a little bit, and I'll leave jotting it down for you and explain it next to an example in a minute. But what this does, and again, think the way I always describe how to graph things, start general, build to more specific. So again, start general, build to more specific. What this rule allows us to do is simply find out how many zeros or intercepts a function will have. And what it does, it's simply by counting the number of sign changes that a polynomial has. Fascinating to me, hopefully also to you. But anyway, the rule of signs will, again, tell us how many, not what they are, not where it actually crosses the x-axis, but how many of each type will we have simply by counting sign changes. So what we're going to start in with here is an example of applying Descartes' rule. Find the possible number of real zeros of the following polynomial. F of x is equal to x cubed minus 2x squared plus x minus 4. Okay. So again, I always like to go with a visual, and we're not graphing this one. We're just simply asking how many types of zeros am I going to have based on Descartes' rule of signs. So real quick, just to show what this might look like. If I have a cubic function, hopefully that's something that we can think about in our mind pretty easily, but it's maybe going to do something like this. Okay. And again, I don't know that, but at the very least, back to section 2, I know it is going to start in quadrant 3 and end in quadrant 1. Now, from this picture, maybe even you can get an idea. We might get 3 places where it crosses the x-axis. It might be less than that, but possibly 3. And here's how we figure that out. With Descartes' rule, look at the original function, f of x. Okay. Count the number of times that the polynomial changes sign. So from going positive to negative or negative to positive. What I do is start here. All right, so let's count. This is a positive term, and I go from a positive to a negative term. That tells me there's 1 sign change. Now this term is negative, and I move to another positive term. There's a 2nd sign change. Next, positive to negative again, there were a total of 3 sign changes. So what this tells me is that the number of sign changes is equal to the number of possible positive roots. So what this tells me is that there could be 3, and I'm going to fill this in also, or 1 possible positive roots. Okay, now why did I put 3 or 1? So the number of sign changes was 3. That tells me I might get 3 positive answers. The reason why it's 1 also is that I also must account for this note in the method. It is the number of positive possible roots or an even number less. So what I had to do then, an even number less than 3, even number you want to think of is 2. 3 minus 2 is 1. And let's say this number were actually 7. What I would actually say then is I just keep subtracting 2 until I get all the way down to 1 or 0. So if there were 7 possible roots, I would have 7, 5, 3, or 1 possible positives. So in this case, it is going to be 3 or 1. That tells me the positives. Part 2 of the rule here's what I do next. Part 2 of the rule, I find f of negative x. So what I'm going to do is I'm going to take the original polynomial, I apologize, kind of work right to left here, but what I'm going to do is I'm going to replace each x with its negative, and then use exponent properties. So f of negative x is equal to negative x cubed, again fill them all in parentheses for the time being, minus 2 times negative x squared plus negative x, so I'm just going to go ahead and make that minus x minus 4 at the end. Okay, so we're now focused on this second polynomial. Using exponent even or odd rules, here's what I do. F of negative x is equal to negative to an odd power would still be negative. Negative to an even power would be positive, so that minus 2 is going to be there, times positive x squared, minus x, minus 4. Okay, so now what we do, to find out, last part, we learned how many possible positive roots there were by counting the original sign changes. If I now count the sign changes in the negative of this polynomial, that will tell me the possible negative roots. And hopefully you can see right away, this does not change sign at all. Negative to negative, negative to negative, negative to negative. So that tells me if I were to go through and find out what my x-intercepts of this polynomial would be, I know that there would be 0 possible negative roots. Okay. So if I got a solution, let's say I were going through and solving, and I got an answer like x equals negative 3 as one of my intercepts, I know it's wrong, just based on this simple sign check that we're able to do with these problems. Okay? So, just one of those for now. It is going to get built into future examples later on in this section. The next part. The zeros theorem. Okay, so the zeros theorem is very simple. The max number of zeros or roots of a polynomial is equal to its degree. Okay, so very simply, not to, this is a very quick and easy application, but if I looked at the previous example that we did and I asked what is the maximum number of x-intercepts that this could possibly have, or the maximum number of zeros or roots, the answer would be 3. It's always equal to its degree. Okay? So again, something very quick, an easy piece of knowledge, something that's very easy to tell when we're working with polynomials. Next part in your notes, you can continue right on through. So we're just going to see a bunch of simple, small checks that allow us to build our knowledge of polynomial graphs and what they would look like if we were to actually go through the graphing process. The next part is the rational root test. Okay, rational root test, and what this does. So again, I've learned 2 things now this section. I learned how can I tell how many possible positive or negative solutions. I don't know anything other than that, and I can also tell how many maximum solutions will I get. And again, that's based on what is the degree, or the highest exponent of the equation. The rational root test lists all potential roots of a polynomial. Okay, so again, now we're talking about what are these specific numbers that could be the x-intercepts or the solutions of a polynomial. Here's how you find it. kind of the letters of the abbreviations I'm going to use here for this one. P are going to be all factors of the constant. All factors of the constant, so the number that is at the end of our polynomial with no variables. Q is going to be all factors of the leading coefficient. So Q, all factors of the leading coefficient. And finally, P over Q is going to be all, and this will be kind of the culmination of the test, all potential real roots. Okay. All right, so we'll do one quick example of applying this test. Using the rational root test, find all potential real roots of f of x equals x squared plus 4x plus 6. Okay. So here's all I do. I simply take my factors of p, which is going to be the constant, 6, and I just think of factor pairs. So that's going to be, think 1 and 6, 2 and 3. Multiply to give you 6. The only other thing you have to account for is that we also have negative numbers. Negative 2 times negative 3 could also give me 6. So when I list these factors, I always must include their positive and negative possibility. So factors of 6 in numerical order, not that you have to. Plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. So all of the factors of our leading coefficient. Next part, Q. Q is going to be the factors of the leading term. It's a 1, pretty easy. The only factors of 1 are itself, so plus and minus 1. So for my my potential real roots, those intercepts or those solutions are going to be simply when I divide all combinations of P by all combinations of Q. Again, this is pretty easy because if I divide any of these numbers by 1, I'm still going to get the exact same list as P. So it's going to be plus minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So once again, that final list of numbers, those are the numbers that could be solutions or intercepts of this polynomial here. So the last thing in this video that we're going to see is an example of just using each of these 3 rules on the same polynomial. We'll say answer the following for f of x is equal to 2x cubed plus 11x squared minus 7x minus 6. Okay. So again, if you were good with those tests that I just ran, feel free to do the same thing for these. That's what I'm going to go through in this example. See if you get what I do at the end. First question, what is the max number of solutions? And once again, the answer to this is very simple. It's whatever the degree of the equation is. In this case, it is a 3. So the max equals the degree, which equals 3. And there's the answer to part A. Part B, use Descartes' rule to find the number of possible roots. All right, so once again, this is always going to involve two parts. I look at the original polynomial. F of x, I'm just going to recopy. It's 2x cubed plus 11x squared minus 7x minus 6. And I simply count the number of sign changes. This tells me the number of possible positives. So I go positive to positive, no change. Positive to negative, one change. Negative to negative is also not a change. So this concludes that this polynomial, and again, this rule has to hold if I were to go through and find them, this one has one possible positive root. So one possible positive root. Part two of this rule, once again, as we did in the first example today, what is f of negative x? So once again, I'm just replacing each x in my original with its negative. 2 times negative x cubed plus 11 times negative x squared minus 7 times negative x minus 6. And use our exponent properties once again to evaluate. A negative cubed is still negative, so I'm going to attach that negative out front with the 2. So negative 2x cubed. Negative squared is positive, so that's going to stay positive 11x squared. Negative 7 times negative x is plus 7x minus 6 at the end. And once again, to finish this test off, we are now going to count the sign changes of the negative polynomial. Negative to positive is 1, positive to positive is nothing, positive to negative is a second sign change. So once again, this results in knowing that this will have either, so once again, there are two changes. So 2 or an even number less than that. 2 or 0 real negative roots. All right. So there is our Descartes' rule of sign test. Part C. Find all potential roots. Find all potential roots. Once again, this is now the P over Q test. So, first of all, factors of, just to the left of the part here, of 6. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Factors of Q, we have a couple now actually, so remember Q, factors of the leading term, that's 2, or negative 2. Well, I guess the original was a 2. But either way, it does not matter. Factors of 2 are 1 times 2. So here's where this now changes a little bit. When I do my final list of possibilities, I must now also think of them being divided by 2. Okay, so remember, it's all combinations of this list divided by this list. So what you can think, these are still going to be there, of course, because I'm dividing them all by 1. So that's still going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. But now, let's go left to right and think of each one divided by 2 and see if that changes things. So the first one, 1 divided by 2 is a half. So that's something new. I add it to the list. Plus or minus 1/2. Oh, sorry. Next, 2 divided by 2 is 1, but I already have that. No need to include it. Next one, 3 divided by 2 is 3/2. I do not have that yet. So plus or minus 3/2. Last one, 6 divided by 2 is 3, and once again, that's already up there. So those would be the lists of all potential roots using the rational root test. So again, later on, the next video with this section is going to be how do we put all of this together to now come up with what are the solutions of a polynomial. And again, there'd be suggested homework with each part of the section.